Right now, as you hear this, a 1-ton machine built in the late 1970s is farther from you than anything humans have ever made, and it is still moving away, permanently. That machine is Voyager 1, and by the time you watch this, it is roughly 170 astronomical units from the Sun. That's about 25 billion kilometers, or around 15 to 16 billion miles. But before we continue, please subscribe to the channel to give your support. Let's continue. An astronomical unit is just the average distance from Earth to the Sun, about 150 million kilometers, 93 million miles. So when you hear 170 AU, you can read that as 170 Earth-Sun gaps in a row. Voyager is that far out. If you try to reach it with normal life speeds, nothing works. Take a car at 100 kilometers per hour, around 62 miles per hour, never stopping, no traffic, no brakes, just straight line motion. At that speed, getting to Voyager would take over 2.8 million years. You could run the entire history of human civilization from the first cities until now, and you still would not arrive. That is the scale you are dealing with before this video even really starts. So then the obvious question comes up. If it is that far, how do we still talk to it at all? How does any signal get there and back? Every command you send to Voyager rides on radio waves, and those radio waves move at the speed of light. Light is the fastest thing allowed by physics, about 300,000 kilometers every second, roughly 186,000 miles per second, and even that is barely adequate now. With Voyager at about 170 AU today, light needs more than 23 hours to go one way and close to a full day for a round trip. In late 2026, Voyager 1 is expected to cross a neat milestone, about 1 light day from Earth. 1 light day is the distance light covers in 24 hours, which works out to around 25.9 billion kilometers, about 16.1 billion miles. When that happens, any command you send, even a simple ping, goes out, travels almost 24 hours, reaches a spacecraft the size of a small car, the spacecraft responds, and then you wait almost another 24 hours for the reply to reach your antenna on Earth. You press send today, you see the consequence tomorrow, and then the confirmation the day after. That delay means controlling Voyager is not like flying a drone. It's more like sending instructions by very slow mail. Engineers tell it what to do, then they live an entire day of normal life before they even know if it understood. If something goes wrong, there is no quick reaction. You're always working with yesterday's spacecraft. From your point of view, Voyager is permanently out of sync with your present. So if the distance and the signal delay are that extreme, what kind of speed does a probe need to reach this position in just a few decades? And is that speed actually good enough for the distances between stars? Voyager 1 is moving at about 17 kilometers per second relative to the Sun. That's around 61,000 kilometers per hour, or 38,000 miles per hour. For everyday life, that number is almost absurd. It is more than 1,000 times faster than a fast-running horse, around 70 times faster than a typical passenger jet. At that speed, you could go from New York to London in a couple of minutes. Voyager reached that velocity using gravity assists, flying close past Jupiter and Saturn and using their gravity fields like ramps to gain extra speed, without ever firing a giant engine. But on interstellar scales, this speed is still painfully slow. At 17 kilometers per second, Voyager needs over 17,000 years to cover 1 light year, just the distance light crosses in a single year. The closest star to the Sun, Proxima Centauri, is about 4.2 light years away. At Voyager's current speed, if it were aimed directly at Proxima, the trip would take on the order of 70,000 years. So yes, inside the solar system, this probe is unbelievably fast, but compared to the distance between stars, it is crawling. That leads to another key point. With such a slow crawl on stellar scales, has Voyager at least fully left the solar system, or is it still under the Sun's influence in some way? Voyager 1 has already crossed one major boundary, the heliosphere. The sun constantly blows out a stream of charged particles called the solar wind, plus a magnetic field, and together they create a huge bubble around the solar system called the heliosphere. Think of it as a big region where the sun's particles and magnetic field dominate. As you go farther out, that wind runs into the very thin gas existing between stars, called the interstellar medium. At some point, the solar wind pressure drops enough that the interstellar medium pushes back, and that boundary is the heliopause. In August 2012, at a distance of about 121 astronomical units from the Sun, Voyager 1 crossed that heliopause. Measurements showed a sharp change in particle counts and magnetic field behavior, matching what physicists expected when you move from the Sun's bubble into interstellar space. That means that today, Voyager 1 is not just beyond the orbit of any planet, it is beyond the main influence of the solar wind. It is directly inside the interstellar medium, feeling the magnetic field and cosmic rays of the broader galaxy more than the ones from our star. Gravitationally, the Sun still holds it, but magnetically and in terms of particle environment, it is now a visitor in the space between stars. So at this point, you have a strange picture. A one-ton machine from the 1970s, around 1 light day away by 2026, running at 61,000 kilometers per hour, outside the Sun's protective bubble, and still sending signals that take almost 2 days for a full conversation. The next question is the one this whole video is built around. When you ask how far will Voyager 1 travel before it stops forever, what exactly are you calling stop? Does it stop when the power from its nuclear batteries drops too low to run a science instrument, sometime in the 2030s? Does it stop when the deep space network on Earth can no longer pick up its extremely weak radio signal buried in the noise? Does it stop when the small hydrazine thrusters fail and the high-gain antenna can no longer stay pointed at Earth, so the signal misses us completely? Or does it only really stop when physics finally robs it of that 17 km per second speed? Maybe because millions or billions of years from now, it is captured by a star or a planet or even a black hole. You are going to break that word stop apart in the rest of this series, layer by layer. In the next part, you will see that Voyager has a power death, a communication death, a steering death, a software death, and then a deep physics reality where none of those deaths actually stop its motion. The normal line you hear, Voyager will die in the 2030s, is only the first and smallest of those endings. And that sets up the core tension for everything that follows, because the distances linked to those different stops are wildly different. One ending happens around the couple hundred astronomical units, another at thousands of AU, another at tens of thousands, and another only when you start counting millions of years and entire galactic orbits. So when does Voyager 1 actually end, for real, not just as a headline about mission will end in the 2030s? You can't talk about how far it will travel until you decide what stop even means, because Voyager doesn't have one death, it has several. First, you have the power stop, the moment the lights really go out. Voyager 1 runs on 3 radioisotope thermoelectric generators, RTGs, each packed with plutonium-238. When it launched in 1977, those 3 units gave it about 470 watts of electrical power, like a few bright household bulbs combined. Plutonium-238 decays with a half-life of about 87 years, so every year the heat output drops, the RTGs cool slightly, and the electrical power falls by a few watts. After almost 50 years, the available power is down to well under half of the original, under about 250 watts, and still shrinking. NASA has already started doing power triage, shutting down heaters and science instruments to keep the most important ones alive. In 2025, they even turned off the cosmic ray instrument on Voyager 1 to save a few more watts. Sometime in the 2030s, there just won't be enough power to run any science instrument at all, even with everything else stripped down. At that point, Voyager stops acting as a working observatory. It might still have a weak transmitter and a basic clock running for a while, but the science mission is dead. If your definition of stop is stop doing science, that ending is around the 200 astronomical unit mark, roughly 30 billion kilometers, about 19 billion miles from the sun. But what if it still has a little power after the last instrument and the radio can stay on a bit longer? Then the next failure mode kicks in, the communication stop, when Earth effectively lets go. Voyager's main transmitter is only about 23 watts, similar to a dim light bulb, but it sends that power through a high-gain antenna that focuses the radio beam. On our side, we use the Deep Space Network, the DSN, a set of huge antennas on Earth, including dishes 70 meters across, about 230 feet. That combo is sensitive enough to pick up Voyager's signal across tens of billions of kilometers. The problem is basic geometry. As Voyager gets farther away, the radio wavefront spreads out in a sphere, and the intensity at Earth drops with the square of the distance. Double the distance, the signal strength goes down by a factor of 4. Triple it, and you're down by a factor of 9, and so on. Even if the hardware on Voyager stays healthy, there's a point where the signal gets so weak that in practice, it disappears into the background radio noise from our own electronics, from the galaxy, and from the sun. Mission planning suggests we can keep pulling usable data into the early to mid-2030s if the RTGs cooperate. Maybe stretch engineering data out toward the mid-2030s, but after that, even a working Voyager would be functionally mute to us. So if your definition of stop is we can't hear it at all, even as a faint carrier tone, then Voyager stops for humanity somewhere in the 200 to maybe 250 AU range, still roughly 30 to 40 billion kilometers out. Of course, you only get that far if you can keep the spacecraft pointed correctly, which brings you to the control stop, the steering death. Voyager has to keep its big dish antenna aimed very precisely at Earth. To do that, it uses tiny thrusters that puff out hydrazine, a chemical propellant, in very short bursts, measured in milliseconds. Over the years, some of those thrusters started to clog, probably from residue building up in narrow lines and valves. By 2017, the primary attitude control thrusters were getting weak, so the team did something wild. They fired up some backup trajectory correction thrusters that hadn't been used since 1980, and they worked. In 2024 and 2025, engineers did more swaps and even revived backup roll thrusters that had been considered dead since 2004 just to keep the antenna aligned. But there is no third backup beyond that. Every thruster now is single string, no redundancy. Eventually, the hydrazine will either run out or the lines will clog to the point where the spacecraft can't correct its orientation anymore. When that happens, Voyager will slowly drift off pointing. The dish will no longer be aimed at Earth, and the radio beam will miss us completely. The transmitter might still be on, burning the last watts, but it'll be shouting into empty space. If your stop is it can't point home even if power and radios work, then that death probably lands in the same general era as the late power decline and the communication limit, sometime in the 2030s to maybe early 2040s at broadly similar distances. Then there's a more subtle failure mode, the data stop, when Voyager's brain forgets how to talk to us, even though the hardware is technically still there. Voyager 1 carries 3 main computers, built with 1970s technology, with a total memory of about 68 kilobytes. In late 2023, something hit the Flight Data Subsystem, the FDS, the computer that packages measurements into data frames for transmission. Suddenly, the spacecraft started sending back a repeating pattern of ones and zeros, no readable telemetry at all. Engineers eventually traced it to a fault in one memory chip in the FDS, likely a stuck bid from a high-energy particle, or just physical wear from decades in deep space. That one damaged section broke the whole data pipeline. To fix it, the team had to move code out of the bad memory region and spread it across the remaining healthy parts, while deleting old, unused routines, like code for Jupiter flyby data, to free up space. With only tens of kilobytes to work with, this is extremely tight. After months of work and a series of commands, Voyager gradually resumed sending engineering and then science data in 2024. That episode is a warning. The computers are old, the memory is tiny, and the space environment is full of radiation. Sooner or later, a fault will hit a piece of code that we cannot move or work around, or it will take out a device we absolutely need for telemetry. At that point, Voyager might still have power, the thrusters might still work, the radio might still be on, but the information reaching us will be nonsense forever. If your stop is the onboard software can't send real data anymore and we can't patch it, that end could arrive even before the last watt runs out. Now, after all of that, power stop, communication stop, control stop, data stop, you are still left with one more layer, the physics reality, where none of those things actually stop Voyager's motion. In interstellar space, there's no air drag like you get in the atmosphere, and the gas between stars is incredibly thin, only about 0.1 to 1 hydrogen atom per cubic centimeter. That density is much lower than any vacuum chamber on Earth. Collisions with those rare atoms do not slow a one-ton spacecraft in any noticeable way, even over millions of years. Once Voyager was accelerated to its current speed, about 17 kilometers per second, there's no built-in reason for that speed to fade. Without a big gravitational encounter or a direct hit with something massive, it will keep going in roughly the same direction at roughly the same speed for a time span that makes human history look like a glitch on a timeline. So you end up with a split answer. Power ends in the 2030s. Communication ends somewhere between the 2030s and 2040s. Control and software can fail at any point in that window. All of those are very real deaths for the mission, but none of them are a physical stop. For the actual journey through space, Voyager outlives its power system, its radio link, and even our civilization. It just keeps moving. The next step is to ask a harder question. Before all of those systems fail, how much more distance can Voyager cover while it is still doing real science, still sending data you can use? And how far out is it when the very last useful bit of information arrives on Earth? There's a hard countdown running on Voyager 1 right now, and it has nothing to do with distance. It's all about how long the power source can keep pushing out watts. You and Voyager are basically racing radioactive decay, and decay is winning. Voyager's power comes from 3 radioisotope thermoelectric generators, RTGs, each one centered on a chunk of plutonium-238. As that plutonium decays, it throws off heat. The RTG bolts that hot side to a cold side, and thermocouples in between turn the temperature difference into electricity. No moving parts, no spinning turbines, just solid-state hardware sitting there, turning nuclear decay heat into volts. At launch in 1977, the 3 RTGs together produced about 470 watts of electrical power. That was enough to run a full payload of instruments, heaters, computers, and the transmitter. Because plutonium-238 has a half-life of about 87 to 88 years, the power drops by a few percent each decade. That sounds slow, but over nearly 50 years, it adds up. Today, Voyager 1's RTGs are down to well under half that original power, losing something like 4 watts every year. That is the slow squeeze that is killing the mission. So what do you do when the power keeps falling but the hardware still wants electricity? You start cutting. NASA has already been doing a kind of slow-motion triage on Voyager. Over the years, they've shut down instruments that are less critical for interstellar science, like some of the ultraviolet instruments and the imaging system. Then heaters on components that could survive colder temperatures, all to keep the most important sensors and the transmitter alive. Every shutdown is a trade-off. You save a few watts here so you can feed the plasma wave instrument, the magnetometer, or the cosmic ray detector a little longer. In more recent years, they even started turning off heaters that kept certain fuel lines and instruments warm, accepting more risk of failure just to claw back a handful of watts. In 2025, Voyager 1's cosmic ray instrument was turned off for power reasons, a clear sign that the endgame has started. Each of these steps buys a bit more distance, but it also strips the mission down, layer by layer. Now link that power slide to distance, because that is what you actually care about. Voyager 1 is moving outward at 3.5 to 3.6 astronomical units per year, so roughly 520 million kilometers per year, around 330 million miles. That speed has been very stable for decades because there's no real drag out there. Take its current distance and add that annual step size into the early 2030s, and you get a rough position of about 200 to 210 astronomical units from the Sun when the last science instrument dies. 200 astronomical units is about 30 billion kilometers, roughly 19 billion miles. That is the scale of science death, the point where no sensor on the spacecraft has enough power to switch on and make a real measurement, even if everything else is still technically wired and intact. But science instruments are not the only power draw, and they are not the only thing that can still matter. After the last sensor shuts down, there's a phase where Voyager becomes basically a health and status beacon. The engineering goal then is to keep the transmitter, the basic housekeeping electronics, and the attitude control alive for as long as the RTGs can supply even a modest current. That bare bones configuration drops science but still sends you data on temperatures, voltages, and system status. Internal NASA estimates put that engineering-only phase stretching a few more years beyond the last science shutdown, maybe into the mid-2030s if nothing else fails first. By then, Voyager is still covering the same 3.5 AU per year, so you're talking well over 200 AU from the Sun, solidly beyond Pluto's orbit, deep in the local interstellar medium. In that window, every watt counts. The transmitter itself needs power. The computer that formats the data needs power. The heaters that keep propellant lines from freezing need power. As the RTGs fade, the team has to choose what drops first. Maybe you cut heaters and accept colder hardware. Maybe you lower data rates. Maybe you let some subsystems go partially out of spec to stretch the life of the core radio. Each decision nudges the odds that something will fail in a way you cannot recover from. And remember, every adjustment you send takes almost a day to arrive, so even the power management strategy runs with a built-in delay. Eventually, you hit a final threshold. At some point, there just isn't enough power to run a stable clock, a radio, or even a reliable onboard computer state. The spacecraft does not explode, it does not freeze instantly, it just quietly falls below the minimum electrical life support line. From our point of view, the signal goes flat and never comes back. When that happens, the RTGs are still physically there, still warm compared to the deep space background, but they're just warm rocks bolted to a metal frame. Voyager transitions from an active spacecraft to a passive mass. No science, no engineering telemetry, no commands in or out. It's just hardware drifting through space, powered only by inertia and gravity. So if you define your question very narrowly, how far does Voyager 1 get before it stops doing useful science? The answer looks like this. Roughly 200 astronomical units from the Sun, on the order of 30 billion kilometers or 19 billion miles out, sometime in the early to mid-2030s. If you broaden it slightly to how far before it stops sending any recognizable data at all, you add a few more years and a bit more distance, maybe tens of billions of kilometers beyond that. Those numbers are already far outside anything else we've ever operated. But those are still short-range answers compared to what the spacecraft will physically do afterwards. Even with dead RTGs, dead instruments, and a silent transmitter, Voyager will keep its 17 kilometers per second speed, and it will keep moving through the galaxy for timescales that no current technology on Earth can match. The next question is, even if we squeeze every last watt out of the RTGs and push the communication gear to the edge, is there a hard line where our biggest antennas on Earth simply cannot hear Voyager anymore, no matter how carefully we manage the power on board? How do you know exactly when a spacecraft dies, when its heart is just a radio signal you can barely hear at all? With Voyager 1, you actually lose it twice, once when it stops talking, and then again when Earth simply can't listen anymore. Start with the basic problem: power versus detectability. Voyager's radio is tiny in everyday terms. The transmitter is on the order of 23 watts, literally in the same range as a dim household light bulb. That power feeds into a high-gain dish on the spacecraft, about 3.7 meters across, roughly 12 feet, that focuses the radio beam into a tight cone aimed at Earth. On our side, the Deep Space Network uses huge dishes, 34 meters wide at the smaller stations and up to 70 meters, about 230 feet at the largest, to catch that beam. So you have a weak bulb on Voyager and a giant, extremely sensitive ear on Earth, tuned to very clean radio frequencies with very little interference. That combination is why we can still hear Voyager after it has passed 170 astronomical units from the Sun, more than 25 billion kilometers, roughly 16 billion miles. But there's a hard rule that no amount of clever engineering can dodge. As the distance goes up, the signal strength drops with the square of that distance. If you double the distance, the power per square meter at Earth drops to 1/4. Triple the distance, it's down to 1/9. Voyager is not getting new power or a bigger antenna out there, so every extra AU it travels makes our job harder. Now add noise. The Deep Space Network is good, but it's not listening in a perfect vacuum. There's radio noise from the galaxy itself, from the Sun, from Earth's atmosphere, from our own electronics. The DSN receivers and signal processing software dig Voyager's signal out of that mess using long integrations and error correction codes. But all of that only works while the spacecraft's signal sits above a certain threshold, the noise floor. Below that, the data stream turns into random bits. NASA's planning for Voyager assumes two trends happening at the same time: the RTGs slowly losing power each year, and the distance increasing by about 3.6 AU per year, around 520 million kilometers, or 330 million miles out. Right now, there's still enough power to run a few instruments and the transmitter, and the DSN can still decode real data. But push those curves out far enough and you hit a wall, a point where even if Voyager's hardware were magically frozen in perfect condition, the combination of low transmit power and huge distance makes the signal effectively undetectable. Current estimates say the RTGs might support engineering data until roughly 2036. Around that time, another limit kicks in. After about 2036, both Voyager 1 and Voyager 2 are expected to be beyond the practical reach of the Deep Space Network altogether. That doesn't mean physics forbids reception, it means that in the real world, with real antennas, real budgets, and real noise, the signal is too faint to pull out in any useful way. Translate that into distance. At 3.6 AU per year, by the time you get to the late 2030s, Voyager 1 is somewhere around 200 astronomical units from the Sun, give or take a bit, depending on the exact year you pick. 200 AU is about 30 billion kilometers, roughly 19 billion miles out. That's about 200 times the Earth-Sun distance, and way, way beyond the orbit of any planet. That range is basically Voyager's radio horizon for us, roughly where the Deep Space Network stops being able to hear even a healthy spacecraft. But you don't lose everything all at once. Before the line goes completely flat, there's a final, weaker phase where we might only detect a bare carrier tone. Think of it like this. When things are working well, Voyager's signal carries digital data, ones and zeros that encode instrument readings, status bits, timestamps. Our receivers lock onto the carrier frequency and then decode the modulation to extract that information. As the signal-to-noise ratio drops, the first thing that fails is the detailed data. Error correction can't keep up, bits flip too often, packets get corrupted. At that point, engineers may still see a spike at the right frequency in the spectrum, a faint, steady tone that tells you the transmitter is on, the antenna is roughly pointed at us, but the content riding on that tone is gone. We already saw a preview of how fragile that layer is during the 2023 to 2024 flight data subsystem glitch. For months, Voyager 1 was sending back a signal that our antennas could lock onto, but the data itself was garbage, a repeating pattern caused by a bad memory chip. It took careful detective work and a series of commands to move code away from the damaged region before usable telemetry came back. That was a software problem close to home, but it showed you there is a real difference between we have a carrier and we have data we can read. In the final years, those issues stack. The RTG power is dropping. The onboard electronics are aging, the thrusters are clogging, the distance is rising, and the DSN has to juggle other missions too. There will likely be a point where the best the network can do is see that faint carrier bump above the noise, with no real telemetry left. After that, even the bump goes away, and the frequency band where Voyager used to live turns into empty spectrum again. When you reach that moment, Voyager 1 doesn't change physically in any dramatic way. The spacecraft is still there, around 200 plus AU from the Sun, still moving at about 17 kilometers per second relative to the Sun, about 61,000 kilometers per hour, 38,000 miles per hour. But for us, it has effectively stopped existing. There is no more feedback, no more status, no more "we sent a command and got a reply 2 days later." From Earth's point of view, it's now a silent object we once knew intimately and can no longer check on. So you get two endings that look similar in distance but feel different. One, the power stop, when Voyager can't keep its own systems alive, and another, the radio stop, when our antennas and receivers can no longer dig its weak voice out of the background. Both happen around the same broad region, a couple hundred astronomical units out, tens of billions of kilometers away, but they're not the same thing. One is about the spacecraft's internal limits. The other is about our limits. Here's the key tension you're building toward. When that last signal drops below the noise and Voyager vanishes from our screens, does anything about its motion actually change? If nobody can track it, does it slow down? Does it drift to a halt? Or does something else, much weirder, happen over the next millions of years? Here's the twist that breaks your normal intuition about motion. Once Voyager 1 goes dark to us, its speed basically does not change at all for longer than our species has existed so far. All the power problems, all the radio problems, none of that hits the brakes. In deep space, stopping is almost not a real option. Start with what Voyager's actually moving through. The space around the Sun, outside the heliosphere, is not truly empty, but it is close. The interstellar medium out here has a density on the order of about 0.1 to around 1 hydrogen atom per cubic centimeter, depending on the exact region. That means you could take a box the size of a sugar cube, put it in front of Voyager, and inside that box you'd have maybe a few dozen to a few hundred atoms. In a lab vacuum chamber on Earth, you're dealing with many orders of magnitude more particles than that. So when Voyager plows through this gas, atom by atom, the drag force is so tiny that you can safely round it to 0 over any human timescale. Collisions with individual atoms barely scratch its paint in terms of speed change, even over millions of years. So if the gas is that thin, does anything really push against Voyager strongly enough to slow it down in a noticeable way? Right now, relative to the Sun, Voyager 1 is moving at about 17 kilometers per second, which is around 61,000 kilometers per hour, about 38,000 miles per hour. That velocity is basically locked in. There is no engine running anymore, but there is also no air drag, no ocean drag, no road friction. The only small adjustments come from tiny gravitational tugs as it passes through slightly uneven regions of the galaxy's gravity field. Those tugs might bend the path a little, but they do not cancel the speed. You can think of it this way in very simple terms. Voyager 1 was pushed up to escape speed by its rocket and gravity assists from Jupiter and Saturn, and now it's just coasting. If nothing big hits it or captures it, it keeps that speed indefinitely, just changing direction slightly over time. It's like sliding on an ice rink that has no walls and no friction, except the rink here is measured in light years instead of meters. So with that speed locked in, how far can it actually go just by coasting if you let the clock run? At its current speed, Voyager 1 takes roughly 17 to 18,000 years to cover a single light year. That sounds slow compared to the idea of light itself, but watch how the distances build when you multiply by large times. In 1,000 years, it travels about a 17th of a light year, around 0.05 to 0.06 light years. That's on the order of 500 plus billion kilometers, hundreds of billions of miles. In 10,000 years, multiply that by 10, and you're close to about half a light year, roughly 5 trillion kilometers. After a million years at the same speed, you're talking about something like 50 to 60 light years of distance relative to the sun, which is tens of quadrillions of kilometers. Remember, this is with no new engine burns, no fuel, just coasting. Once you accept that drag is basically zero, distance is just speed times time. And if speed is steady, the numbers scale up linearly. So the longer you wait, the farther Voyager gets, with no built-in stopping point. At this stage, you might ask the obvious question. If the sun's gravity reaches out forever, doesn't it eventually pull Voyager back, or at least slow it enough that it stops escaping? The sun's gravity does extend infinitely, but what matters is how fast Voyager went when it left the region of the giant planets. There's a specific escape speed at any distance from a mass, the minimum speed you need so that gravity can never quite pull you back into orbit or fall in. After its flybys of Jupiter and Saturn, Voyager 1 was put on a hyperbolic trajectory, meaning it had more than enough speed to escape the sun's gravitational hold. The sun is still pulling on it, which is why its path is a gentle curve rather than a straight line, but the pull is never strong enough to reverse the outward motion. The same logic applies to the planets it already passed. Their gravity bent its path, but did not trap it.
So yes, gravity is still there, but the job it's doing now is just reshaping the route, not canceling the escape. Voyager is not on a long, slow loop that comes back to the solar system. It is on a one-way track outward, always moving away, just with a very slight arc when you draw it on a galaxy map. At this point, the idea of stopping in the normal sense falls apart. For Voyager's motion, there is no realistic stop button built into the physics. There is no friction in the vacuum to bleed off its kinetic energy. There is no automatic braking force waiting in interstellar space. The only things that could truly stop it are very unlikely events, like a direct collision with a dense object, or a close gravitational capture by a star, planet, or compact object at just the right geometry to remove most of its speed. Over millions or billions of years, small gravitational nudges can change its direction a lot, but they don't magically bring its speed down to zero. So if you take all of this seriously, you shift your question. You started with how far will Voyager travel before it stops forever, but its speed doesn't stop on any human timescale. The more accurate version becomes, how far can Voyager go before something in the universe finally interrupts that motion? Which is a much harsher, much larger question. And that sets up the next step, because even though Voyager has escaped the heliosphere and will keep its speed for millions of years, it still hasn't cleared the true outer structure of the sun's domain. There is one more gigantic region to cross, the Oort Cloud, and the distances and times there are on a totally different level from the few hundred astronomical units you've been talking about so far. Most people hear interstellar space and think Voyager has left the solar system already. That sounds neat, but technically it hasn't even reached the sun's real outer wall yet. If you care about the full size of the system the sun controls, Voyager is still on the way to the frontier. First, you need a clear picture of what the Oort Cloud actually is. The planets, the asteroid belt, even Pluto, sit in a flat disk-like region close to the sun, maybe out to 50 astronomical units or so. Beyond that, models and comet orbits point to something much bigger, a vast, roughly spherical shell of icy bodies surrounding the sun from about 2,000 AU out to something like 100,000 AU. That structure is the Oort Cloud. At the outer edge, 100,000 AU is roughly 1.5 light years, almost half the distance to the nearest star system, Alpha Centauri. We have not imaged the Oort Cloud directly, but the orbits of long-period comets strongly suggest a huge reservoir of icy objects that get nudged inward occasionally, fall toward the inner solar system, then swing back out. That is the region Voyager is headed toward. So when does Voyager actually reach this thing if it is moving at only a few astronomical years per year?
Right now, Voyager 1 adds about 3.5 to 3.6 AU of distance per year, roughly 520 million kilometers, 330 million miles every year. NASA estimates that at that pace, it will need on the order of 300 years from now to reach the inner edge of the Oort Cloud. 300 years times about 3.6 AU per year gives you about 1,080 AU of extra distance. Add that to Voyager's current position, and you are in the ballpark of a couple of thousand AU from the Sun, which is where the inner Oort Cloud is thought to begin. So for the next few centuries, Voyager is still just crossing the relatively empty region between the heliosphere and the start of that comet reservoir. Once it reaches the inner Oort Cloud, the timescale jumps. To get from the inner edge, around a few thousand AU, out to the outer parts, maybe tens of thousands of AU, you're talking about a path length that is tens of thousands of AU. At 3.6 AU per year, it takes on the order of tens of thousands of years. Rough estimate, 30,000 years to really move through and out the other side. That is why NASA says it will take something like 30,000 years for Voyager to fully exit the Oort Cloud's main population. During that time, it never slows in any meaningful way. It just keeps adding AU after AU. Put those distances into simpler terms. 2,000 AU is already more than 2,000 times the Earth-Sun distance. 10,000 AU is 10,000 times that. By the time Voyager has crossed the Oort Cloud 30,000 years from now, it could be sitting tens of thousands of AU away, well over half a light year from the Sun, corresponding to at least several trillion kilometers, and actually more like tens of trillions if you convert the full number. At that point, the planetary region the orbits of Mercury through Neptune, are a tiny dot around the Sun compared to the volume Voyager has covered. Saying it left the solar system at 200 AU really undersells how large the Sun's actual gravitational domain is. There is a natural worry when you hear cloud of icy bodies. If the Oort Cloud is full of comets, doesn't that mean Voyager is flying into a minefield? The answer is no, not in the way your gut might picture it. Yes, the Oort Cloud is the main source of long-period comets that drop into the inner solar system from steep tilted orbits. Those comets get nudged from their orbits by passing stars, by the tidal pull of the Milky Way, or by other small perturbations, and some of them end up on paths that bring them close to the Sun and Earth. But cloud is misleading. The Oort Cloud is still extremely sparse. The individual icy bodies are separated by huge distances. Even if there are trillions of objects total, they are spread over a sphere with a radius measured in tens of thousands of AU. The density is so low that the probability of Voyager hitting one specific object is effectively zero on realistic timescales. Statistically, Voyager will just pass through the region, with only slight gravitational tugs from distant masses changing its path by tiny amounts. So if you decide to define solar system boundary in a strict way, as the distance where the Sun's comet reservoir and long-term gravitational influence effectively end, then the story changes from the earlier numbers you heard. In that strict sense, Voyager leaves the Sun's realm only when it exits the far side of the Oort Cloud, not when it crosses the heliopause, and not when it passes Pluto's orbit. That means the solar system stop, for this definition, sits tens of thousands of years in the future, at thousands to maybe tens of thousands of AU from the Sun. Compare that to the earlier stops you've already seen. The science stop happens around 200 AU, roughly 30 billion kilometers. The communication stop also lands in the same region, when the deep space network can't hear anything anymore. But the solar system boundary stop is much farther out, thousands to tens of thousands of AU, on the order of half a light year or more away, on a timeline of tens of thousands of years. That contrast is important. When someone says Voyager left the solar system in 2012, they are using the heliopause definition, which is valid for magnetic and particle environment. When you use solar system in the sense of all material gravitationally bound to the Sun, you need to push that exit way out in both distance and time. And once you accept that, you can zoom even further out. Because even after Voyager clears the Oort Cloud, it still isn't really interacting with just empty space. On long enough enough timescales, it starts to approach other stars, other neighborhoods, and the distances there are measured in light years, not astronomical units. So after the Oort cloud, what does next even mean for Voyager when the only things left out there are other stars? The first real test of that comes in about 40,000 years, when Voyager gets its first close neighbor that isn't the Sun. The target, in this case, isn't some famous bright star. It's a dim red dwarf called Gliese 445 in the northern constellation Kemala-Pardalis. Right now, Gliese 445 is about 17 light-years from Earth. Calculations based on both orbits show that in roughly 40,000 years, Voyager 1 will pass within about 1.6 light-years of that star. That is still a huge distance in human terms, but on a galactic map, it counts as a near miss. Here's the key part. Voyager isn't aimed at Gliese 445 in any active way. What actually happens is that Gliese 445 is moving toward our solar system at roughly 119 kilometers per second, far faster than Voyager's 17 kilometer per second speed, and Voyager is moving outward on its own trajectory. Over tens of thousands of years, those two motions line up so that their paths bring them relatively close, so the encounter is mutual. The star comes toward the region where Voyager is headed, while Voyager continues its one-way escape. It's more like two cars on different highways crossing near the same junction than one car steering toward the other. By that time, where is Voyager relative to the Sun? At about 17 kilometers per second, or around 61,000 kilometers per hour, Voyager needs around 18,000 years to cover 1 light-year. After around 40,000 years, it will have traveled on the order of a couple of light-years relative to the Sun, so something like 20 trillion kilometers of straight-line distance, give or take. That's about 12 trillion miles. These numbers are approximate, but they give you the scale. This is far beyond the Oort cloud region you just talked about. The Sun at that point is a distant star behind it, not a dominant source in its local space. There's a subtle point here, though. When you talk about straight-line distance, you are picking the Sun's frame as your reference. In the actual galaxy, the Sun itself is moving at about 220 kilometers per second around the galactic center, looping once every roughly 230 million years. Voyager shares almost all of that motion because it was launched from the Sun's neighborhood. So if you track its actual path in the galaxy's frame, it's not a clean straight line. It's a kind of long, stretched helical track, riding along with the Sun's orbit and slowly drifting away from it. But when you ask how far has it gone from us, that 2 or so light years is the useful number. So does getting within 1.6 light years of another star actually do anything? Does Voyager get a gravity assist, a real slingshot, or even a chance of being captured? At that kind of distance, the answer is basically no. 1.6 light years is still tens of thousands of times farther than the distance from Earth to the Sun, and far outside the interplanetary region of Gliese 445. Gravitational force drops very fast with distance. At 1.6 light years, the pull from Gliese 445 on Voyager is tiny compared to the pull from the combined mass of the rest of the galaxy. Practically, all that happens is a very small deflection of Voyager's trajectory, a tiny change in direction that you would need careful calculations to even notice. There is no dramatic flyby, no sharp slingshot maneuver, no sudden spike in speed. The spacecraft doesn't fall in, and it doesn't come anywhere near any planets that might orbit Gliese 445. That leads to the bigger point. There is no realistic star crash in Voyager's near future, even on tens of thousands of years. The Milky Way feels crowded when you look at it in photographs, but most of that brightness is just line-of-sight stacking. The average distance between stars in our region is measured in light years. The actual radius of a star like the Sun is only about 1 million kilometers, which is tiny compared to the distances between stars. If you scatter a few 100 billion stars in a disk more than 100,000 light-years across, the probability that a 1-ton spacecraft on a random hyperbolic path directly hits one of them is extremely low. Even across millions of years, the most likely pattern is what you're seeing with Gliese 445, a sequence of near misses. Voyager passes stars at distances of 1 to a few light years, maybe gets weak gravitational tugs that slowly redirect its path, but nothing that counts as a collision or capture. Studies of future stellar flybys show another pass with a different star cataloged as TYC 3135-52 at less than 1 light year in about 300,000 years. Again, that is still vast space between the probe and the star. So if you want a single number for this whole section, here it is. By about 40,000 years from now, Voyager 1 has traveled several light years relative to the Sun, tens of trillions of kilometers of path length, and it passes within about 1.6 light years of Gliese 445, skimming the outskirts of another stellar neighborhood. It doesn't slow down, it doesn't get captured, it doesn't burn up. It just gets its trajectory nudged slightly and keeps going. And that should push your sense of scale out again. 200 AU and 30 billion kilometers cover the end of science and communication. Thousands to tens of thousands of AU cover the Oort Cloud, tens of thousands of years into the future. Now you're talking about tens of trillions of kilometers and multiple light years just to reach the first modestly close star encounter, and Voyager is still basically untouched. The obvious next step is to ask what happens when you stretch the clock even further. If 40,000 years only buys you a couple of light years and one near miss, what does 100,000 years look like, or 300,000 years? At that point, your normal sense of time breaks, but Voyager is still just doing the same simple thing, moving forward at the same speed. On a 100,000-year clock, Voyager has covered roughly 5 to 6 light years relative to the Sun. That is about the distance from the Sun out past the Alpha Centauri system and a bit beyond, deep into the local stellar neighborhood. In straight distance, that's on the order of 60 trillion kilometers, around 40 trillion miles. This is the kind of number where the units almost stop mattering. But the important point is this. On that timescale, Voyager is no longer just beyond the solar system, it is among the nearby stars. While all of that is happening, it is also crossing through a specific piece of galactic real estate. Right now, the Sun sits inside a region called the local bubble, a patch of space filled with low-density, hot gas, likely carved out long ago by supernova explosions. This bubble spans hundreds of light years. As Voyager moves out, its path threads through different parts of the structure. While its instruments are still alive, it can sample magnetic fields, charged particles, and plasma densities that tell you how the local bubble is shaped. Once those instruments die, it still passes through these regions, but now it's just a silent mass. The gas and fields are still there, Voyager is still moving through them, but no one is left to log the values. Stretch the timeline further, to around 300,000 years. By then, one more near miss shows up in the calculations. Projections suggest that Voyager will pass within less than 1 light year of another star, an M dwarf, cataloged as TYC 3135-52-1. Less than a light year is closer than the current distance to Proxima Centauri, so in stellar terms, this is a legitimately close pass. But just like with Gliese 445, it's still not enough to count as a real interaction. The star's gravity at that distance is much too weak to pull Voyager into an orbit or perform any dramatic slingshot. At best, it nudges the trajectory by a tiny angle. The spacecraft keeps going. It doesn't stop, it doesn't crash, it doesn't get captured. Even on 300,000-year timescales, all you get is a list of almosts. Now think about what hundreds of thousands of years of exposure do to the spacecraft itself. Out there is no air, no rain, no oxygen, no classic rust. There is also no shielding from micrometeoroids, cosmic rays, and interstellar dust. Tiny dust grains, moving at tens of kilometers per second, will occasionally slam into Voyager's surfaces and chip away microscopic bits of metal. Over enough time, that pitting and erosion adds up. Cosmic rays, which are high-energy particles, will continue to punch through the structure and the electronics, depositing energy, breaking bonds, damaging materials at the atomic level. Exterior surfaces will darken, get rougher, and lose fine details. But because there is no atmosphere or liquid water, there is nothing to drive large-scale chemical weathering. Bolts don't dissolve. Aluminum panels don't flake away in the same way they would on Earth. The golden record, which is a gold-plated copper disc mounted on the outside, was specifically designed with this environment in mind. The golden coating helps resist erosion from charged particles and microscopic impacts, and the information on it is stored mechanically as grooves. Over hundreds of thousands or even millions of years, it will get scarred, but there's a good chance that large portions of its surface will still be physically readable, at least in principle, if someone or something capable of precision analysis ever picks it up. So on these mega-year scales, Voyager's identity shifts. It is no longer a functioning mission. It is a fossil. If any future civilization finds it, whether that is a distant descendant of humans or some completely unrelated species, what they get is a preserved artifact of late 20th century Earth. The design of the antennas and electronics, the manufacturing marks on the metal, the record and its engraved diagram, all of that is a snapshot of our technological adolescence. From their point of view, Voyager is like a piece of rock that drifted in from another part of the galaxy. Except this rock has machine geometry and a deliberate message etched into it. The important thing here is that none of this changes its basic motion. After 100,000 years, after 300,000 years, after however many micrometeoroid hits and cosmic ray strikes, Voyager is still on roughly the same outbound track, moving at roughly 17 kilometers per second relative to the Sun. The interstellar medium is still too thin to slow it. It hasn't burned any new fuel, no continuous force has been acting on it to drag it down, its kinetic energy is basically untouched. The path curves gently under the pull of the Milky Way's mass, but the magnitude of its velocity stays almost constant. So now you've seen what far means at 40,000 years, and then at 100,000, and then at 300,000. You've watched the mission fade, the instruments go quiet, the near misses with stars begin, and the spacecraft turn into a drifting fossil. The question you have to ask next is what happens when you push the clock even harder, not just hundreds of thousands of years, but a full million years and beyond. At that point, any human timeline is gone, but the spacecraft is still doing the same thing, moving forward at basically the same speed. At its current speed, over about 1 million years, Voyager travels on the order of 50 to 60 light-years relative to the Sun. You can think of that as roughly 57 light-years as a typical number. 1 light-year is about 9.5 trillion kilometers, around 6 trillion miles. So 50-plus light-years is tens of trillions of kilometers multiplied by tens again. In straight-line terms, that range takes you from the Sun, past the Alpha Centauri system, and out across a big chunk of our local stellar neighborhood. Inside a sphere about 100 light-years across, centered roughly on the Sun, there are thousands of stars, and probably many dozens of planetary systems in the right temperature range for liquid water. Over 1 million years, Voyager has had the chance to pass near that whole cluster of stars, always missing, always drifting past, but sharing the same part of the galaxy. Now, zoom out one level more and look at this in galactic context. The Milky Way disk is about 100,000 light-years across. Compared to that, 50 to 60 light-years is tiny. That's roughly 0.06% of the full diameter. So even after 1 million years of travel at 17 kilometers per second, around 61,000 kilometers per hour, 38,000 miles per hour, Voyager has crossed only a thin slice of the galaxy. It has gone far from the Sun, yes, but relative to the entire galactic disk, it has barely moved. It is still in roughly the same broad region, the same spiral arm segment, the same general band of stars. And there is another big motion happening underneath all of this that you have to keep in mind. The Sun is not fixed in space. It orbits the center of the Milky Way at roughly 220 kilometers per second. That's close to 800,000 kilometers per hour, about 500,000 miles per hour. One full orbit around the galactic center takes something like 230 million years. Voyager shares almost all of that motion because it was launched from the sun and only got an extra 17 kilometers per second from our rockets and from the gravity assists. That means the dominant speed in the galaxy's frame is not Voyager's own 17 kilometers per second, but the sun's hundreds of kilometers around the core. So when you ask, how far did Voyager go, you have to be clear about the reference frame. From the sun's point of view, you subtract the sun's motion and just look at Voyager's relative velocity. In that frame, after 1 million years, the spacecraft is tens of light years away, something like 50 to 60 light years. That's a meaningful separation. From the galaxy's point of view, both the Sun and Voyager have done roughly the same thing. They have moved along nearly the same orbit around the center, completing only a tiny fraction of one full circle. The extra speed Voyager has compared to the Sun just makes it slowly drift outward along a slightly different path. In that frame, you would say it has shifted a small distance from the Sun's track, not flown across the disk. This is where the basic idea of distance starts to get slippery. The Sun is orbiting, the nearby stars are orbiting, Voyager is orbiting. Everything is in motion inside the galaxy's gravity field. If you stay in the Sun's frame, the distances growing between the Sun and Voyager are tens of light years over 1 million years, and you can list out all the local stars it passes. If you stay in the galaxy's frame, the change looks small, a minor offset in one orbital path. Both descriptions are correct, but they answer slightly different questions. What does not change in any of these frames is the key fact about Voyager's speed. Barring some extremely unlikely collision or very close encounter with a compact object, after 1 million years, it is still moving at essentially the same 17 kilometers per second relative to the Sun. The interstellar medium is still too thin to slow it. It hasn't burned any new fuel, no continuous force has been acting on it to drag it down, its kinetic energy is basically untouched. The path curves gently under the pull of the Milky Way's mass, but the magnitude of its velocity stays almost constant. So after this million-year step, you keep coming back to the same conclusion. In terms of the mission and our ability to hear it, Voyager is long gone. In terms of the solar system, it is far outside any practical boundary. In terms of the local stars, it has crossed a decent chunk of space and passed by thousands of potential targets. But in terms of motion itself, there is still no realistic stop. It keeps going. That raises the next level of the question. If 1 million years only gets you across a tiny fraction of the galaxy, what happens when you extend the timeline another 1,000 times to 1 billion years? At that scale, the Sun's own future starts to look uncertain. Earth's surface may not even be habitable anymore, and galaxies aren't standing still either. The real tension becomes not just how far does Voyager go, but can Voyager actually outlive the planet that launched it? If 1 million years already feels ridiculous, jump 3 steps higher, to 1 billion years. On that timescale, you're not comparing Voyager to missions or civilizations anymore. You're comparing it to the lifetime of Earth itself. Start with the raw distance. Earlier, you saw that over about 1 million years, Voyager covers roughly 50 to 60 light years relative to the Sun. You can keep 57 light years in your head as a typical value. Now, scale that up by a factor of 1,000. Over 1 billion years, at basically the same 17 kilometers per second, Voyager travels on the order of 57,000 light years relative to the Sun. That number is already at the scale of the Milky Way's visible disk, which is roughly 100,000 light years across. So in 1 billion years, if you just track the separation between Voyager and the Sun, you're talking about distances where the probe could plausibly be on the opposite side of the galaxy from where the Sun started, or at least scattered to a completely different region of the disk. But that doesn't mean Voyager draws a straight line from one edge of the galaxy to the other. Remember, the Sun itself is orbiting the galactic center at around 220 kilometers per second, and one full orbit takes roughly 230 million years. Over 1 billion years, the Sun completes about 4 to 5 full trips around the Milky Way. Voyager shares almost all of that motion, so it's not cutting across a static background. It's riding along with a swirl of stars, gas clouds, and dark matter. Gravitational nudges from passing stars, giant molecular clouds, and the overall structure of the galaxy will slowly change its orbit, pushing it slightly inward or outward, maybe giving it a bit more tilt above or below the galactic plane. So over a billion years, instead of one clean chord, you should picture Voyager weaving in and out around the sun's general track, ending up somewhere else in the disk, still bound to the galaxy's gravity well. Now, compare that to what is happening back home on Earth over the same billion-year stretch. The sun is slowly getting brighter as it ages, roughly 10% more luminous every billion years or so. That extra energy pushes Earth's climate harder and harder. At some point around 1 billion years from now, maybe a bit earlier, maybe a bit later, depending on details, models say Earth's surface likely becomes too hot for liquid oceans to remain stable. Water in the atmosphere increases, greenhouse effects amplify, and you can end up with a moist or runaway greenhouse where the oceans evaporate and the surface conditions become hostile to complex life. The continents, the mountains, even the crust itself keep moving on geological timescales, but the biosphere as we know it today probably doesn't survive. Humans are long gone in any normal scenario. The entire idea of our civilization is ancient history. Meanwhile, Voyager 1, a machine from 1977 with less onboard memory than a cheap calculator, can still exist. Not powered, not transmitting, not doing science, but physically there, as hardware. Out in the galactic disk, some tens of thousands of light years of path length away from its starting point relative to the sun, its structure is slowly eroded by micrometeoroids and cosmic rays, but big chunks of metal and the golden record can still be intact enough to recognize as artificial. In that strict sense, yes, Voyager probably outlives Earth's habitability, and it may even outlive many of the physical traces of human technology on Earth's surface, which will be recycled by tectonics and erosion. You might wonder whether a billion years of exposure doesn't almost guarantee that something catastrophic happens to a one-ton probe. The odds are not zero, but they are still surprisingly low. The chance of Voyager directly colliding with a star over a billion years is extremely small because stars are tiny compared to the distances between them. Even getting close enough to a star or a massive planet to be fully ripped apart or captured into a tight orbit requires very specific geometry, usually involving multiple bodies to shed kinetic energy. Passing through a dense molecular cloud could, in theory, slow it a bit more than the thin interstellar medium, but even there, the drag is spread over huge distances and long times. The more realistic outcomes are less dramatic. It might get hit by a modest-sized rock, big enough to break off antennas or damage the bus, but not to vaporize everything. It might just keep taking hits from small grains, slowly chewing up surfaces. Or nothing major happens at all, and it remains more or less intact, just more pitted and darkened. At this point, when you say how far does Voyager travel before it stops, and you're talking about a billion-year horizon, stop is no longer about power or antennas or even local encounters. The limiting factor becomes the long-term evolution of the galaxy itself. Over a billion years, stars orbit, spiral arms shift, gas clouds form and collapse, and the Milky Way changes shape. Voyager is now just one tiny test mass inside that huge dynamical system. Its future distance is effectively tied to how long the galaxy remains in something like its current configuration, which leads directly to the next step. If you keep running that clock forward, the Milky Way itself does not stay isolated. It has a scheduled encounter with another galaxy, Andromeda, in a few billion years from now. So the question stops being just, can Voyager outlive Earth, and becomes, can Voyager ride out a full-on galaxy collision and still keep going? At this point, far doesn't just mean outside the solar system or beyond the local stars. You're now asking if a one-ton probe from 1977 can live through a full-on collision between galaxies. And the answer is, very likely, yes. Start with what's coming for our galaxy. The Milky Way and Andromeda are on a collision course. Current estimates say the first major encounter happens in about 4 to 5 billion years from now. Their mutual dark matter halos are already interacting. Their mutual gravity is pulling them together, and eventually the two spiral disks will plunge through each other, then swing back and do this multiple times before they settle into a single merged system, often called Milky Way in the literature. Stars in each galaxy are extremely far apart compared to their sizes, so when the disks interpenetrate, you don't get stars physically smashing into each other in huge numbers. You get orbits scrambled, gas clouds shocked, and long tidal streams of stars flung out. Gravity, compared to that, is basically a grain of dust hanging in the Milky Way's outskirts. When the collision unfolds, it won't plow into a wall, it will just come along for the ride inside the combined gravitational field. So where is Voyager by then? Fast forward 4 to 5 billion years. By that time, relative to the sun's starting position, Voyager has had time to move tens of thousands of light years, because that 50 to 60 light years per million years adds up when you multiply by thousands of millions. On top of that, the sun itself has completed maybe 20 or more orbits around the galactic center. In practice, this means that Voyager's current distance from the sun number is almost meaningless on that timescale. The sun might have moved into a different part of the merged galaxy. Voyager might have been scattered to a different radius or height away from the disk. But both are still inside the combined gravitational well of Milky Way plus Andromeda. Voyager becomes one of countless small debris fragments, stars, gas clouds, dead planets, rogue comets, and other stripped material, all orbiting the center of the new, larger galaxy. Now look at what the gravitational chaos actually does to Voyager's path. Every time a star passes relatively nearby, or Voyager crosses a region with extra mass like a dense star cluster or a big molecular cloud, its orbit gets tweaked slightly. You can think of it as a long, slow, random walk in orbital energy and direction. One encounter nudges it outward a bit, another tilts it relative to the disk, another drags it a little inward. Over billions of years, those small changes can add up. Voyager might be shuffled from the galactic disk into the thicker, puffier helopopulation, or it might migrate between different orbital radii. The key detail is, nothing in this process looks like a clean braking maneuver. Gravity is reshaping the track, not taking away all the speed. So does it ever actually get kicked out of the galaxy completely? That is possible in principle. In a major merger, some stars and smaller objects do get thrown out on escape trajectories, forming long tidal tails and even becoming intergalactic wanderers. For Voyager, which has almost no mass compared to stars, the probability depends on whether it happens to be in the right place at the right time when a strong three-body interaction occurs, for example, between two stars and the galactic potential, or near a massive compact object. Over many billions of years, repeated weak encounters can occasionally add up to enough of a push that its orbital energy exceeds the escape energy of the merged galaxy. If that happens, Voyager stops being a galactic drifter and becomes an intergalactic one, cruising through the space between big galaxy groups. Distances at that point move from tens of thousands of light years to hundreds of thousands, even millions of light years from its origin. If you follow that line all the way, how far changes again. Instead of asking how far from the sun or how far across the Milky Way, you're now looking at separations on the scale of the local group and beyond. A probe ejected from the merged Milkometa could, over trillions of years, move far out into the thin, dark regions between galaxy groups. There, the nearest large mass might be hundreds of thousands of light years away, and gravity would be even weaker. Its speed relative to the local frame would still be whatever it was last given, so it would keep going, with even fewer encounters to disturb it. By this point in the timeline, stopping has nothing to do with Voyager's onboard systems or the structure of our original galaxy. Those are already gone or transformed. The limit isn't its speed, and it isn't our ability to hear it. The hard boundaries come from cosmology itself, dark energy, and the expansion of the universe. As the universe keeps expanding faster and faster on large scales, galaxies, clusters, and superclusters move away from each other, and beyond a certain distance, they recede so quickly that no new signals or objects from them can ever reach us. That's the cosmological horizon. Voyager, gravitationally tied to our local group or to the merged Milkometa system, stays inside that island of matter, but everything outside drifts permanently out of contact. So at this epoch, the question how far until Voyager stops has morphed into how long does large-scale structures stay connected? The spacecraft is not running out of speed. Instead, space itself is stretching. Galaxies are colliding and merging, and dark energy is locking regions of the universe away from each other forever. Voyager is now just a tiny test particle inside that process, still moving, still not stopped, long after the Milky Way, as you know it, has ceased to exist as a separate galaxy. The only logical move after that is to push one more level out. If the galaxy merger and dark energy don't actually stop Voyager, then the final ceiling on its journey has to come from the ultimate limits of the universe itself, from horizons and heat death, and the question of whether anything can keep moving forever in a cosmos that is slowly running out of usable energy. At this point, you're not asking what stops Voyager's mission, or what stops its trip through the solar system. You're asking if the universe itself ever forces it to hit a real wall. To answer that, you have to switch from spacecraft engineering to cosmology. Start with the region Voyager is actually trapped in. The Milky Way, Andromeda, and a few smaller galaxies around them form a structure called the local group. All of that mass is gravitationally bound together. The expansion of the universe is trying to pull everything apart, but inside the local group, gravity wins. Those galaxies orbit each other, merge, and reshuffle, but they don't get torn away by expansion. Voyager is tied to that same gravity well, whether it stays loosely bound to the merged Milky or gets kicked into the local group's outer halo. It's still inside that overall island of matter. It doesn't get dragged out with the distant galaxies that are accelerating away. Now layer dark energy on top of that. Dark energy is a name we give to the thing driving the accelerated expansion of the universe. Because of that acceleration, there is a distance beyond which galaxies recede from us faster than light. Not because they're moving through space faster than light, but because space between us and them is stretching fast enough. Beyond that boundary, called the cosmological horizon, light that leaves today will never reach us. Those regions are effectively cut off forever. Voyager never crosses that horizon because it's bound into the same local group as us. The whole local group, including the merged Milky sits inside one gravitationally bound bubble that does not get ripped apart by expansion. Voyager is stuck with us, orbiting inside that island long after most of the rest of the observable universe has slipped out of causal contact. So if cosmic expansion doesn't slow it down and the local group keeps it, is there any other way for Voyager to really lose its motion? Think about its energy budget. Once the RTGs have gone cold electrically, Voyager isn't emitting much. There's no engine burning propellant, no continuous thrust, no strong radiation beam draining kinetic energy. It's not like a satellite skimming through Earth's atmosphere, bleeding speed as heat. Out in deep space, with no drag and no active propulsion, its kinetic energy is nearly constant. The only changes come from tiny gravitational interactions, where some energy can trade between Voyager and larger masses, which mostly bend the path. They don't systematically drain the speed to zero. So you end up with a short list of ways Voyager could actually stop in the strict physics sense. One, it could collide with something massive enough to absorb a big chunk of its momentum. That would mean hitting a star, a big planet, a large compact object, or something similar. Given how empty space is and how small those targets are compared to the distances between them, the probability is extremely low, even if you wait billions or trillions of years. Two, it could be gravitationally captured by a compact object after a very close pass, for example, passing near a star or a black hole in just the right way that it ends up in a bound orbit. And then over extremely long timescales, that orbit might decay through interactions with other bodies or with very weak radiation processes. To make that happen, you generally need very specific three-body interactions, where Voyager, a star, and perhaps another massive object exchange energy. Again, this is possible in principle, but spectacularly unlikely on anything shorter than enormous timescales. The reality is, long before any of those rare events is almost guaranteed to happen, something else is going on in the background. The universe itself is running down. Stars burn through their nuclear fuel and die, star formation slows as the gas supply is locked up in stellar remnants, galaxies fade as their bright, short-lived stars disappear. Over truly long times, you end up with a cosmos dominated by dim embers, white dwarfs, neutron stars, black holes, and cold brown dwarfs. During that whole process, Voyager is still there as a small, cold object with some residual kinetic energy, moving through a space that is getting darker and quieter. It doesn't lose its motion in any dramatic way. It just becomes harder and harder to notice in a universe that has fewer and fewer structures left that can interact with it. At extreme timescales, after many trillions of years, you start to hit the scenarios talked about in heat death discussions. Black holes slowly evaporate through Hawking radiation, ordinary matter might decay, depending on the physics of the proton, background radiation cools toward absolute zero. In those regimes, the fine details of one probe's trajectory don't really matter because the entire concept of active processes in the universe is fading out. The cosmos is approaching a state where nothing much happens anywhere. So, when you phrase the question as, does Voyager ever hit a wall? The honest answer is this. There's no realistic physical wall that stops its motion on any timescale we normally talk about. There's no drag strong enough, no automatic braking force in interstellar space, no expansion threshold it can cross that suddenly cancels its speed. Instead, its journey is limited by something else. The lifetime of structure in the universe. Long before Voyager's motion really damps out through rare collisions or captures, the stars will be gone. The galaxies will be quiet, and the universe will be sliding toward a thin, cold end state. That flips your original question. You started by asking, how far does Voyager go before it stops forever? At this stage, the more accurate line is Voyager doesn't stop, the cosmos does. The probe's motion outlasts its power, outlasts our ability to hear it, outlasts Earth's habitability, probably outlasts the Milky Way as a recognizable spiral. The only thing that can truly end its journey is the same thing that ends everything else, the long-term evolution of the universe itself. And yet, even now, you haven't answered another practical question. Compared to all the other probes we've launched, is Voyager really that special, or do future spacecraft completely blow past it and make this whole story just an early chapter? So, if Voyager 1 is this extreme outlier in distance and lifetime, how does it stack up against everything else we've actually thrown outward and against the ships we dream about but haven't built yet? Start with the most obvious challenger, New Horizons. New Horizons is the Pluto probe, launched in 2006. After its Jupiter gravity assist, it's cruising at about 14 kilometers per second relative to the Sun, a bit slower than Voyager 1's roughly 17 kilometers per second. In speed terms, that's still huge, around 50,000 kilometers per hour, about 31,000 miles per hour. But it's not enough to catch Voyager. New Horizons has newer tech, better instruments, and a more modern design, but it started later, and it didn't get the same chain of gravitational boost that Voyager picked up from both Jupiter and Saturn. In the race for farthest from the Sun, Voyager had a 30-year head start and slightly higher cruise speed. That combination keeps it ahead for a very long time. Then look at the other escapees, because Voyager 1 isn't alone on the way out. Pioneer 10 and Pioneer 11, launched in the early 1970s, are also on escape paths out of the solar system. Voyager 2, launched a few weeks before Voyager 1, is on an escape trajectory as well, but in a different direction, heading toward a different patch of interstellar space. All of them are trailing behind Voyager 1 now. They each have slightly lower speeds and different exit vectors, so over time the separation grows. If you map the question, how far before they stop, they all share the same basic physics story you've been walking through. RTGs die, radios fade, the deep space network loses them, they cross the heliopause, they coast through the Oort Cloud, and they drift between stars. Voyager 1 is just the tip of the spear, the one that happens to be slightly faster and therefore slightly ahead on that whole path. Now, compare that to what we think we could build but haven't yet. On the drawing board, there are concepts like solar sail probes pushed by powerful laser beams from Earth or lunar bases, which could in theory reach a significant fraction of the speed of light. There are fusion-powered starship designs where controlled fusion reactions drive the exhaust to push a spacecraft to hundreds or even thousands of kilometers per second. At those speeds, you could cross a distance to the nearest star in decades instead of tens of thousands of years. But all of that is theoretical right now. No fusion rocket has flown, no laser sail at that scale exists. The engineering hurdles and energy requirements are enormous.
In the real world today, the only probes that are actually in or near interstellar space are the ones you already know: Voyager 1, Voyager 2, and, just inside the heliosphere's outer regions, the others on the way out. Voyager 1 is the first human object to cross the heliopause and operate in the true interstellar medium. It's likely to be the first to reach a full light day of distance from Earth. That is a permanent historical milestone. Even if a future mission launched with a far better design and blew past 17 kilometers per second, it can't take away the fact that Voyager did it first, with 1970s hardware and a few kilobytes of memory. That gives Voyager a unique claim to distance that doesn't go away just because the numbers change later. It is the first probe to leave the sun's protective environment and never comes back. And somehow, that first try is already set up to outlive every bridge, every city, every satellite, every server farm humanity has ever built on Earth. Long after our newest missions have gone silent, this old spacecraft is still out there, following the same trajectory, carrying the same golden record bolted to its side. So your narrative, you should frame Voyager as the prototype interstellar ark. It's not our fastest possible ship, not our smartest, not the most efficient design we could dream up. It's our first try at building something that truly leaves the sun's protective environment and never comes back. And somehow that first try is already set up to outlive every bridge, every city, every satellite, every server farm humanity has ever built on Earth. Long after our newest missions have gone silent, this old spacecraft is still out there, following the same trajectory, carrying the same golden record bolted to its side. So the key question is, how long can that record stay readable, not in theory, but under real deep space conditions? Out where Voyager is going, you have a few main threats to any material. There is no air, so there's no oxygen to cause normal rust. There's no liquid water, no storms, no atmosphere to sandblast it. Corrosion in the Earth sense is almost gone. Instead, the problems are micrometeoroids, cosmic rays, and occasional hits from interstellar dust grains. Micrometeoroids are tiny bits of rock and metal, often smaller than a grain of sand, moving at tens of kilometers per second. When one hits the spacecraft, it can chip off a microscopic crater. Over hundreds of millions of years, a lot of those hits can roughen the surface and erase fine detail. Interstellar dust grains, slightly larger, do the same thing with more impact energy. Cosmic rays are high-energy particles that slam into atoms in the metal and can gradually damage the lattice structure or cause displacement at the atomic level. Even with those threats, deep space is still a very gentle environment compared to any planetary surface. There's no constant abrasion by air, no rain cycles, no temperature swings driven by day and night on a planet. The golden record is plated in gold, which is chemically very stable, and the copper underneath is not sitting in a corrosive bath. Some modeling work done when the record was designed suggested that the grooves could remain physically readable for hundreds of millions of years, possibly up to billions of years, especially for the parts of the surface that are oriented toward the spacecraft and get some shielding from direct particle hits. The mounting bracket and the spacecraft structure itself act as partial armor, blocking some directions of incoming dust and radiation. Now compare that to how long Earth keeps physical evidence of us. Earth's crust is constantly recycled by plate tectonics. Oceanic plates get pushed under continental plates and melted. Mountain ranges erode, sediments get compressed, buried, lifted, and worn down. On those timescales, tens to hundreds of millions of years, a huge amount of the surface record gets destroyed or deeply buried. If you ask, how much of today's human infrastructure will still be clearly visible in 100 million years, the answer is very little. Maybe some deep mines, some altered mineral layers, some isotopic signatures, but most buildings, roads, and even cities will be gone or unrecognizable.
Voyager's golden record, drifting in a vacuum with no tectonics and no weather, has a real chance to outlast the geological memory of our civilization on Earth's surface. That's a strange inversion. The fragile disk in space is more durable in some ways than continents. Tie that back to distance. Earlier, you saw that over about 1 billion years, Voyager can move on the order of 57,000 light-years relative to the Sun, a distance comparable to the Milky Way's diameter. If the grooves are still readable after that, and the metal hasn't been completely chewed up by impacts, then in principle, the message is still intact while the spacecraft has crossed almost the entire galaxy. That means the limiting factor for how far does this message reach is not the lifetime of the material, it's how much galaxy the probe can cross before the cosmic environment itself stops being friendly to complex structures. If you push the timeline even more into multi-billion-year ranges, you can imagine scenarios where Voyager gets scattered by gravitational encounters, maybe even kicked out into intergalactic space after the Milky Way Andromeda merger. In that case, the golden record is no longer just crossing a spiral disk, it's drifting through the dark between galaxies. As long as the metal hasn't been completely shredded, the information is still there, hidden in grooves on a plate, far from any star, carrying a snapshot of Earth that no longer exists. So, if you define how far does Voyager travel not as how far until the engines stop or how far until the RTGs die, but as how far can our message physically survive in a readable form, your answer jumps to galaxy scale. You're talking tens of thousands of light years minimum, maybe hundreds of thousands or millions of light years if the spacecraft ends up in intergalactic space and keeps going. The range of the message is basically the distance the spacecraft can cover before either the record is destroyed by chance impacts or the universe evolves to a point where there's no one left to find and decode it. That brings you right back to the heart of your original question. You started with simple numbers, a couple hundred astronomical units, a few tens of billions of kilometers, and asked how far until Voyager actually stops before it stops forever. What answer are you really asking for? The mission's end, the solar system's edge, or the end of motion itself? Start with the smallest scale, the first hard stop, the science stop. In the 2030s, as the RTGs fade, there's a point where the last working instrument simply can't get enough power to turn on. At Voyager's current speed, that happens when it's a bit over 200 astronomical units from the Sun, roughly 30 billion kilometers away, around 19 billion miles. At that point, no more magnetic field data, no more plasma measurements, no more cosmic ray counts. It stops being a science mission and becomes a powered spacecraft that's only capable of basic housekeeping and maybe a few engineering readings. If your definition of stop is stop doing experiments, then the answer is brutally short. It stops around 200 AU, barely outside the heliosphere on the scale of where it will eventually go. Then you get the second layer, the communication stop. A few years after the science dies, sometime between the 2030s and maybe the early 2040s, the combination of falling RTG power and increasing distance pushes Voyager's radio signal below what the Deep Space Network can work with. That's probably in the same ballpark of distance, maybe 200 to 250 AU, still on the order of 30 to 40 billion kilometers, a couple of hundred times the Earth-Sun distance. After that, even if a transmitter is technically still on, even if some electronics are still alive, our antennas can't pick out that whisper from the background noise. From our point of view, Voyager disappears. If your stop means we can't hear it, can't track it, can't tell if it's alive, then that's where it stops existing for humanity, at a few hundred astronomical units. Now jump to the true structural edge of the Sun's domain. The solar system stop. Using the Oort Cloud definition, the solar system doesn't really end at the heliopause or at Pluto's orbit. It stretches out into a huge diffuse shell of icy bodies that runs from a couple of thousand AU to maybe 100,000 AU. Voyager needs roughly 300 years just to reach the inner Oort Cloud, and about 30,000 years to fully pass through it and clear the far side. By then, it's thousands to tens of thousands of AU away, a significant fraction of a light year, easily multiple trillions of kilometers. If you define stopping as it's no longer in the sun's comet cloud, no longer really part of the solar system in any structural sense, then Voyager stops being a solar system object only after tens of thousands of years, at distances that make the 200 AU radio depth look tiny. Push out further to the nearby star stop. Over 100,000 to a few 100,000 years, Voyager 1 passes multiple stars at distances of 1 to 2 light years, Gliese 445 after about 40,000 years, then later an M-dwarf like TYC 3135-52 after around 300,000 years. By the time you're in that range, Voyager has traveled tens of light years relative to the Sun, tens of trillions of kilometers, tens of trillions of miles. It's threaded through the local stellar neighborhood, past thousands of stars if you count everything inside that sphere. And yet, even at this stage, there is still no physical stop. It hasn't collided with a star, it hasn't been captured, its speed hasn't dropped in any meaningful way. If your stop is it has fully left the sun's neighborhood and crossed over into other stellar neighborhoods, then the answer is after hundreds of thousands of years, at tens of light years, and even then the spacecraft is just cruising. Now take the last step, the galactic and cosmological stop. On million-year timescales, Voyager racks up distances of tens of light years. On billion-year timescales, it moves on the order of tens of thousands of light years relative to the Sun, comparable to the diameter of the Milky Way. All that time, it's riding inside the galaxy's gravity well, sharing its rotation, getting its orbit slowly reshaped by close passes with stars and gas clouds. A few billion years out, the Milky Way merges with Andromeda. Voyager survives that as one more tiny piece of debris in the merged system. Over even longer spans, it might be scattered into the galactic halo, or even ejected into intergalactic space by a series of gravitational encounters. On these scales, the only things that can truly end its journey are galaxy-level dynamics over billions of years, or the ultimate long-term fate of the universe: star death, galaxy fading, and heat death. So you end up with a hierarchy of stops, each with a different distance and a different kind of ending. Stop number 1, science stop, early mid-2030s, around 200 AU, about 30 billion kilometers, roughly 19 billion miles. That's where the last instrument dies. Stop number 2, communication stop, late 2030s into the 2040s, roughly 200 to 250 AU, 30 to 40 billion kilometers. That's where Earth's biggest antennas can't hear even a carrier, and Voyager vanishes from our screens. Stop number 3, solar system stop. Around 30,000 years from now, thousands to tens of thousands of AU, a big fraction of a light year. That's where it clears the Oort cloud and you can reasonably stop calling it a solar system object. Stop number 4, nearby star stop. Around 100,000 to a few 100,000 years, tens of light years, tens of trillions of kilometers. By then it has crossed the local stellar neighborhood, passed multiple stars at light-year distances, and still hasn't slowed or been captured. Stop number 5, galactic and cosmological scales. Millions to billions of years, tens to tens of thousands of light years. That's where its future is tied to galaxy mergers, gravitational scattering, and eventually the long-term cooling and dimming of the universe itself. So when someone throws the question at you, how far will Voyager 1 actually travel before it stops forever, you can't just give them one number. You have to answer with a stack. If you mean experiments, it stops around 200 AU. If you mean contact, it stops at a few hundred AU. If you mean leaving the sun, it stops after tens of thousands of years at thousands to tens of thousands of AU. If you mean leaving the neighborhood of nearby stars, it stops after hundreds of thousands of years, at tens of light years. And if you mean motion itself, then in any realistic sense, it doesn't stop at all, not on timescales our species has words for. We built a machine, launched it in 1977, and it is now on a path where it will still be moving, still carrying the golden record long after Earth's oceans have boiled, long after the Milky Way has merged with Andromeda, and long after any memory of the night sky you see today has been erased by the evolution of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.